like Kathy, I looked down and Jerry had gotten up at slide 13, and I think that was about the halfway mark. I couldn't decide what I was going to leave out, so I didn't leave anything out. Yeah. And so, so about slide 13, Jerry, you should get up and start pacing around. But the one thing I don't want to leave out is that thanks to John, that we're all here today, and not only that, he's created a place that for 25 years, it wasn't just a safe place for people from other disciplines to talk to each other. It was actually a place where other disciplines were encouraged to talk to each other, and actually it did happen. So the field of integrated assessment didn't exist when I was in graduate school, although not much existed at that point. But I'm going to begin by saying, what is this? What is this thing? It's a bunch of people that I think for most of you lurk in working group 3 somewhere, and they're sort of like the Jaws music that plays whenever they come out. But what do they do? And part of it, the reason that they're kind of a difficult thing to put your arms around is that they do several different things. And so the integrated assessment models are at their very heart. They're these models that capture these interactions between complex and highly nonlinear systems. And in the end, their value added is that they put the pieces of the puzzle together and they highlight things that you wouldn't have seen if you just pursued disciplinary research independently. They highlight what happens when nonlinear systems collide. And that's kind of, ultimately that's going to be their value added, and that has been their value added, and I think that will continue. But they also are this other thing in which you have the provision of information to the other scientific communities. So they're the place you go to for scenarios, and the scenario business started back with the IPCC in SA90, and over wine I'll tell you the story of SA90. Which is a sad story. But they provide greenhouse gases, emissions, short-lived species, land use, land cover, all of this stuff gridded, and increasingly feature interactions with demographics, technology, and the impacts of climate change. And the other place they show up, so they show up 3 places. They show up in the policy process because they actually are these decision support tools that get used by nations, international organizations, regional decision makers, and private sector decision makers. And so it's a part of the reason it works now. Okay. The other thing that makes them difficult, and you'll see in really prestigious people not realizing that integrated assessment models are not just one thing. They come in 3 different sizes, DICE, medium, and RCP class. And John Wyatt has this running thing. He always puts up an image from the latest Star Trek movie of the Dreadnought class star cruiser. The DICE class models are highly aggregated. They have a relatively small number of equations, literally a handful. I think there were 18 equations in DICE. And were originally built to address this large, multi-generational cost-benefit problem. That's not what I'm going to talk about today. I'm going to talk about the Dreadnought class, or the RCP class of model. And there are only a handful of them. That makes it easier. There are only about a half a dozen. And if you got a model and I failed to put it up and you think it belongs here, then I'm sorry. There are 2 of them in the US. There's 3 of them in Europe. There's 1 of them in Japan. These models were built to better understand the human interactions with the larger biogeophysical and biogeochemical systems. They provide all the information that a state-of-the-art physical Earth system model needs to run a CMIP experiment. So you're going to get all the greenhouse gases, you're going to get all the short-lived species, you're going to get the aerosols, you're going to get land use, land cover. And they're built by interdisciplinary teams. They're not just built by one smart person. And I forget who put this up the first time this morning, but you look at the history of climate model, and you have this history in which the original models were built by one single PI. That's the way the integrated assessment modeling community was at one time. These are all teams of multiple people with backgrounds in multiple disciplines. They have PhDs in a wide variety of disciplines, and I won't go through all the PhDs we have at the Institute, but it's an impressive list. They're physical system models that you have human system models, and we think of them as as that home, but they have physical system models built into them that they run. They range from these simple models like MAGIC, which is kind of the default that you get with an integrated assessment model, all the way up to the CESM. I mean, they run that whole range of models. They have explicit representations of technology, and they've been the workhorses of the community developing emissions and emissions mitigation scenarios. But the big frontier on these models is that they're incorporating impacts, adaptation, and they're becoming models with multi-scale operating systems, and they've begun to look at agriculture, water, forestry, buildings, energy. I'll show you a couple of examples as I go through and as I'm yanked off the stage. There have been traditionally they provide the emissions. I stole this out of the fifth assessment report. And here are the RCPs. This is the latest generation of emission scenarios that are run by the CMIP exercises. And they, 2.6 to 8.5, that was the range that existed in the literature. It spanned the biggest to the lowest forcing that anyone could find, and a couple of intermediate points in the middle. There's also a 300-year extension, which it was really an interesting piece of work, and again, over wine or beer. We'll talk about that. And then we have this, the parallel process, which we are engaged in as a climate research community today. And the IAMs are moving out of that traditional RCP, we're going to feed the climate models, and then we throw that over the transom, as it were. The climate modelers fish it out of the water, do something with it. They clean it, they gut it, they throw the stuff they don't like back in the water, and then they run CMIP. They run CMIP exercises. I'm only a little bit joking. And they run CMIP exercises. That's the way it's been done in the past. Now, you're getting to this stage where the whole system is moving to, it's not just a one-way street to impacts, adaptation. And in fact, this is a system. Humans maybe they might mitigate climate change. At the same time, they are adapting to it. Does that have any consequences? And I think the answer is going to turn out to be yes. But the people who are doing the impacts research actually need scenarios that they can use. These RCPs, they're great if you're a climate modeler. They got all the greenhouse gases, they got land use, land cover, and all that. They got no population. They got no GDP. That's not our case. If you want that information, you got to go back to the original producers of that. And you can get ours for RCP 4.5 off of our website. But, it's a lot of work. It's not archived. The whole idea of this SSPs, shared socioeconomic pathways, and in a sense, I think we owe Richard Moss a debt of gratitude here because he pushed this community to think about this as a bigger problem than we've traditionally thought about it. And so he's pushed us to move toward not just one set of an unmitigated scenario, and then from a very different set of reference scenarios, 3 mitigation cases that are they're not related in any meaningful way, to a set of scenarios, 5 reference cases that are meaningfully related. So if I draw a cartoon of where the climate modeling world was when I was a kid, it was kind of this integrated assessment. They had an economy, there was an energy system. That's about it. There was a carbon cycle that we kind of shared, and then there was climate models, and then there was the people who did impacts, adaptation, and vulnerability research. If you kind of look at the map today, it's changed, in my opinion. It's changed to a world where there's an enormous set of overlapping interests in population, in economy. We share water, we share ice, we share carbon. It's really a much more overlapping and interactive world. And so if you look at the integrated assessment models, particularly in the US, there's an emphasis on these 5 new themes that range from integrated assessment models are going to depend, they're not going to give up what they've been doing in the past, but they're going to do a lot more impacts, adaptation, and vulnerability research. They're going to move to these finer spatial and temporal resolutions. They're going to look at the interactions both across mitigation and adaptation of key inputs or key activities like energy, technology, water, and land. And they're going to look at uncertainty as well as do a lot more work in working with the physical science community. So I'm going to look at GCAM, which is the integrated assessment model that we are responsible for at the Pacific Northwest National Laboratory and the Joint Global Change Research Institute. And I'm going to look at where is it going, because it's going through this transformation, and it hasn't gone through a transformation like this for a long time. This is an enormous transition period. We were evolving rapidly to becoming a modeling system with multiple interoperable modules, temporal and spatial scales, modules of application in response to evolving challenges. So we're looking at new problems, and we're having to change these models to address those new problems. And so tackling problems like climate impacts or this energy, water, land nexus means that we're going to much higher resolution data inputs. We're going to reconciled and transformed data set, and that's a big activity that we've always done. We've never really made those reconciled data sets available to others. We're going to start doing that. We're going to employ interoperable modules and models, so we swap in and out, and then we're going to do a lot more interacting. For example, with Richard, he's down there at the site, and we're up there at the globe, and we're actually going to telescope from one end to the other. We're going to produce output products at appropriate spatial and temporal scales. And so you look at it, there's not just one spatial scale in this model anymore. There's 32 global regions, 283 land regions, 233 water basins, all of which are tracked simultaneously. Oh, but wait a minute, this thing does telescope. And so you run a 50-state version of that. Actually, it's 51 regions because we do the District of Columbia. And then you put this the output is actually down there at half-degree grid, but we actually do 0.05 grids on it as it is appropriate to the problem. And so you're getting output. This is a really interesting study, but I'm not going to take the bait. If you watch over here, this is climate coming back to the energy system. This is climate not coming back to the energy system. This is climate coming back to it. And you can see by the end of the century that not only have each one of the states change, but the national totals in the U.S. are changing. They're changing as a direct consequence of the climate they're going on. We're looking at how the states interact in a global context. And so you can see, here's a set of about half a dozen scenarios that we ran under different climatic conditions, mitigation policy conditions. And that, I'm not going to dive into any of this, but just say that this is the kind of output now that we didn't used to produce. We used to produce global outputs. We're now producing this stuff ungridded. And this is kind of one of the things that's really cool. 2 minutes, I can do that. We do hydrology, we do demand and runoff. We build these up from either from the climatology, or we take, if we're working with Ruby, we take that runoff. We do the demands, we build that up, we build it at a half-degree grid. You do the change. This is what you typically get from the discipline right now. You've got a problem here. You don't have enough water. And so what are we going to do? Well, we're not going to change anything in the models. We're going to let the agricultural systems produce agriculture. We're just going to color this grid red. They ran out of water, but it doesn't have any consequence. So what we've got now is actually a closed system. And the experiments we're doing is really cool, that you've got this scarcity, and finally the scarcity bites. Something's got to give. If there's not enough water, there's not enough water. And you can watch a basin. You just perturb a basin, and you can watch it just propagate through the whole global system, because the demands didn't disappear. They forced the system to change. There's the integrator system model. This is a really great project. Probably the most important thing that came out of it was that, 2 things. One is that coupling is a lot harder than it looks. Secondarily, if you couple the terrestrial system, and these are preliminary results, they just got back last week, but what we see is a different carbon cycle when you have two-way coupling of the terrestrial system in a mitigation scenario like our RCP 4.5. And one of the most impressive accomplishments of the project was getting highly interdisciplinary teams to talk to each other at the same and actually understand what the others were saying. So this is it. That's the end. So basically that's what I said before.
Marty, why don't you come up and cue it up while we ask Jay a question or two. So any questions for Jay? Whirlwind tour through integrated systems.
So I mean, what's being shown is extremely impressive. I mean, the issue in the evolution of thought. What I mean, just very generally, what would you say is the policy receptivity to the type? And by receptivity, I mean way more than we showed it to them and they like it. What's been the receptivity from the standpoint of how integrated assessment models enter into decision making? And I'll tell you why I'm asking. I mean, Patty, myself, others are in the IAV community, of which integrated assessment models are one tool in integrated assessment. So what's been the sort of map onto where people are making decisions, or is it just creating a place to talk about risks?
The traditional place that they come in is in emissions mitigation. And so if you look at IPCC Working Group 3, the heart of that assessment report is integrated assessment modeling. What's really interesting and new is that these models are now moving to address new problems. That is, simultaneously mitigating and adapting to an evolving climate, and doing it in a way that is internally consistent. And that's why I find the IESM project one of the most exciting projects I've ever worked on, because its goal is to actually create that. Oops.
Yeah, the consequences of that have been
Yeah. Well, you see, different carbon, the carbon distributed differently in the pools. You're seeing more I won't describe the experiment to you, but you see changes in the system.
Jay, the estimates of greenhouse gas emissions associated with the 4 RCPs are generated by 4 different integrated assessment models. What have you learned from that process about differences between IAMs and how they put the pieces together?
That's a really good question, and it's a long answer. In some ways, the RCP class models have a lot in common, but they also they each grew out of a different root system. If you look at the image model started off with it as an ecosystem model, and it grew in energy and economy that complemented it. If you look at the image model, it actually started off as message, which was an optimal energy supply model. They all have their different, and they all treat things differently. And so it's sort of, each one of them has their own thing that they do really well. One of the things that GCAM does really well is that it's all integrated. There's none of this sneakerware between the land use and the energy system. You can't solve the energy system without solving the land and water systems simultaneously. It can't be done. And so, there's none of this kludging together. And that's we consider that a real strength. The other models will all have a strength that they go to as well. And so, it's in a sense you know the models.
Last quick question.
I was going to ask about the flexibility of this class of models, or your prediction about the flexibility of this class of models to introduce new kinds of data sets, like feedbacks, or let's say you get a better hydrological data set on not a model, but where people actually get their water from, for example, or
Right. And I think that's one of the really exciting new developments, that the models are not just one combination of submodels put together, but as the problem changes, that you actually have this modularity. That is, you swap modules out and move, when you need a more complex model, you actually swap in a more complex model. For most purposes, we use magic. For state of the art, when we're going, we want to really frontier experiment. We're going to run this IESM, and there's a huge difference, and yet, in a sense, it's all this. It's all part of the same research approach.